Hello, ladies and gentlemen, and welcome back to Prospect Charter School's Algebra 1 course. Today we're going over section 7.2, which is one of my favorites because it mixes two of my favorite subjects of all time together. We're going over scientific notation. Now, as you may know, Mr. O'Neill is a bit of a geek and a nerd, and he loves all things science-y and all things mathy. And he loves scientific notation. Scientific notation is the bomb. It makes it so that numbers go from incredibly large or incredibly small to something that is manageable. And if you haven't noticed about mathematicians, we like things that are manageable. So for our scientific notation, we're going to be looking at powers or exponents of the number 10. So today's lesson is brought to you by the number 10. So here's 10. Say hi, 10. Alright, that's enough out of you. Which of course makes him cry when you yell at him, but that's alright. We'll just live with it. Alright, so 10 has different higher powers. He normally starts out with the power of 1, because 10 to the first is, of course, 10. But we also have a power of 0, and as we remember from the previous lesson, anything raised to the 0 power other than 0 itself is, of course, 1. But then things start to get complicated. From there, we're looking at higher powers of 10. So all you atheists out there are higher powers. Get used to it. All right, let's start with 2. 10 to the second power would be 2 zeros after the 1. 10 to the third power would be, yes, 3 zeros after the 1. So are we seeing a pattern yet? How about 10 to the fifth power? Yep, 5 zeros after the 1. How about the number everybody wants to have in their bank account? At least in US dollars. That's right, 6 zeros after the 1. In essence, who wants to be a millionaire? So, what does scientific notation do for us? Well, in science, sometimes the numbers that we deal with are just ridiculously large. For example, the distance between the Earth and the Sun. If you do that in miles, it's a lot. If you do that in meters, it's even more. So to make it so that we're not writing zeros over and over and over and over again, we started using something called scientific notation, which means that we take the powers of 10 and turn it into times 10 to the power of blah. So for an example, let's say that we are trying to take 5 billion and turn it into scientific notation. So for scientific notation, I'll write this down for you. For scientific notation, you take the first number and the next few significant figures, or sig figs, and then multiply by a power of 10. Now I'm thinking I'm missing part of that. Yes, the first number is a whole number. The first number, which will be a whole number, and the next few significant figures will be part of the decimal. Now, I know I've been saying all along decimals are demons, and I firmly believe that. I firmly believe that if you can put it into a fractional format, do so. But if you can't, then, well, you have to deal with decimals. Decimals will never give you an exact answer. They will always give you an approximation. That's why I don't like decimals. I like being exact. I like being correct. I like being right on the money. So with scientific notation, though, and dealing with real stuff, it's never exact. It's never right on the money. There's always some error involved in any kind of scientific experiment or measurement. So scientific notation and the working with decimals is just fine. So how do we turn 5 billion into scientific notation? Let's say that we want to go to 3 significant figures, 3 sig figs. Then I would have 3 numbers total. My first number is my whole number, in this case 5. Then I put a little decimal point, and then I look at the next 2 numbers to get a total of 3 significant figures. My next 2 numbers are very boring, 0 and 0. I then count how many decimal places that I have to go before I reach the number right before 5. So in this case, I'm starting here at the decimal, and I start counting 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have to go 9 places. So I take my 5 and I multiply it by 10 to the 9th power. So this would become 5.00 times 10 to the 9th is equal to 5 billion. So let's look at some other numbers and see how we can do this. Remember, if you're moving the decimal place to the left, it's going to be a positive power. If you move the decimal place to the right, that means it's going to be a negative power. So for an example, let's say that we have 0.000529, and we want to convert that into scientific notation. So to convert this into scientific notation to 3 significant figures, we'll keep the 3 sig figs for now. When in doubt, do 3 sig figs. So to do this one, I know that I need to have 5 as my whole number, and then it's going to be 0.29. So I know it's going to be 5.29. And it's going to be 10 to a power, but I don't know what that power is until I start counting. So I take my decimal place and I see how many places I have to go until I move it to right here. So doing that, I go over 1, 2, 3, 4. 4 places to the right. So this would be times 10 to the negative 4th power. When going to the right, you're moving it to the right, so you're going in. Yeah, it's just weird. Get used to it. When you're going to the right, powers become negative. When you go to the left, powers become positive. Alright, let's try another one, just to confuse you even more. Let's say that we are given 853.4 times 10 to the 5th power. And we want to turn this into proper scientific notation. Currently, is it in scientific notation? The answer to that question is no. No, Mr. O'Neill. This is not a number, a decimal, 2 more things, and then a power of 10. This has 2 more extra numbers in front of it. So that means I need to move my decimal 2 places to the left. So what does that do to my exponent? I've already got a times 10 to the power or something, so what do I do there? Real easy. You add. So this becomes 8.534 times 10 to the original 5, but I moved it over 2 more spaces, so I add 2 more to it. When I do that, I get 8.534 times 10 to the 7th. Mr. O'Neill, what if we have to go the other way? Ah, good question. Very good question. What if we have 0.0163 times 10 to the negative 3rd? Actually, let's make it even more confusing, times 10 to the 5th. Well, then we do the same thing, right? We take our decimal place, and we're moving it to the right 2 spaces. And since it's to the right 2 spaces, we say negative 2. So this becomes 1.63 times 10 to the 5 minus 2, or plus negative 2, depending on your point of view. Whichever way you want to think of it. you could think of it as just 5 minus 2 if you want to. It's not that bad. I don't know why my computer's going berserk. So we have 5 minus 2, which of course is 3, so this becomes 1.63 times 10 to the third power. Now, what about converting back? I know you guys don't like working with scientific notation, but I'll tell you what, it is phenomenally awesome. It is really, it makes stuff that should be like impossibly difficult super easy. Just super easy. And what we need to do, though, is be able to translate back and forth, and then I'll show you why scientific notation is just so flippin' awesome. Okay, let's say that we have 4.53 times 10 to the negative fifth, and we want to convert that into normal notation. Well, to do that, we take our decimal place and we move it in the opposite direction of the one indicated. So this says go to the left because it's negative, which means I'm going to go, well, I am going to go to the left. 1, 2, 3, 4, 5. So it looks like I need to have 1, 2, 3, 4 zeros in front of that 4. So I'm going to go 0.1, 2, 3, 4 zeros, 4, 5, 3. Except I should make the 3 more legible. There we go. What if I have 4.21 times 10 to the fifth? Well, again, we're doing the same thing. We're going to be moving the decimal place, except this time we're going to be going to the right 5 spaces. Whereas before we went to the left 5 spaces, now we're going to the right 5 spaces because it's positive. 1, 2, 3, 4, 5. If we look at it, I need a 0, 1, 2. I need 3 zeros placed in there. So this would become 4, 2, 1, 0, 0, 0. Or 421,000. Okay, so when converting back, go the normal direction. When converting to, go the other way. I guess would be our rule of thumb. Alright, now let's see how this can be used in a manner that makes life easier. I'm not sure if we would be doing, yeah, we're going to be doing that stuff next chapter. But let's say that we look at Jupiter. And Jupiter, good old Jupiter, biggest planet in the solar system that we know of. And the Jupiter planet is 143,000 kilometers in diameter. That makes writing it down over and over and over again really hard, especially if you want to do it in meters, because that would be 143 million meters, which is quite a lot. So what we would like to do is we would like to make it smaller. We'd like to use scientific notation. So for our scientific notation, we need to find out what power we're going to. It looks like we're going to 1, 2, 3, 4, 5. So we go 1.43 times 10 to the fifth. That would be the diameter of Jupiter. What about the diameter of the Earth? Well, the diameter, let's see, Earth is about average distance from the Sun. Oh. How far is the Earth from the Sun? Well, the Earth is 5.91 times 10 to the 8th kilometers from the Sun. What is that in normal terms? Well, I'd have to move it to the right 8 spaces. So I go 5.91 and move it to the right 8 spaces. 1, 2, 3, 4, 5, 6, 7, 8. So we'd have 591, 0, 0, 0, 0, 0, 0, or about 591 billion kilometers, no, million kilometers from the Sun. So yeah, that's some big numbers that we can condense into a smaller space. One of my personal favorite numbers is avocado. No. 6.02 times 10 to the 23rd. This is a number of atoms in a mole. This is used for chemistry a lot, for molar equations, and also to find out how heavy substances are. So moles are really, really awesome. And 6.02 times 10 to the 23rd is how many atoms are in 1 mole. So how many atoms is that? Well, let's write it out. 6.02, and then we have to go over 23 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There we go. I hate to tell you this, guys, but I think this is a rather large number. I think I don't even know the name for the number that's this big. So if we look at it and we start putting commas every 3 spaces, there's thousands, millions, billions, trillions, quadrillions, and I don't know what comes after quadrillions, so your guess is as good as mine. This is where scientific notation really shines, is when you're dealing with stuff like moles and how many atoms you have and the charge of a single electron and that sort of thing, because those numbers are just ridiculously large and ridiculously small. Alright, that's it for scientific notation. It is now time for your bug work. Alright, before you go, bug work. Let's see, we're in section 7.2. Hashtags. Don't you love science? Scientific notation is easy. Let's learn more about higher powers. Let's go 1 through 13 odd. And then 15, 17, 19, 23, 25, 27, 31, 31, 33, and 35. Let's see if there are any more, because, you know, the stuff is so easy that you can get it all done before you leave anyway. And the rest of it's no longer easy. Alright, that's good. That'll be all. Good luck, and have fun.